derive that response. So here you're actually not solving the differential equation, you're going to go through a roundabout method in which we actually gain the total response. Now, reason why we do this within circuits 1 is we want you to walk before you run. Once students go over into circuits 2, then we actually derive everything, the differential equation from the time domain using nothing more than KVL, KCL, and then actually the current voltage characteristics of each element within the circuit. And from there we utilize Laplace transforms and then solve the entire system in the frequency domain outright, and then we just pull it back into the time domain. It's a very, very powerful technique that we utilize. And later on we actually convert the schematic into its Laplace equivalent for a more generalized method of solving these systems. But for now, this actually gives us more of a deep insight into what's going on, especially with the resistance, especially with how we see the time constant actually working. Well, you guys should actually believe me on this stuff. You guys should actually be like, where with this exponential, where does that come from? And I say this time and time and time again, that math does nothing more for us than model that actual physical phenomena. And the physical phenomena that we're looking at right now, guys, is the response to basically an element having an electric field built about it, and that positive and negative charge being built on that anode and cathode. But you guys shouldn't take it from me. Let's go see the response. So we're actually going to take a look at a very, very small resistive capacitive circuit. There's our distillery. And we're going to see if, in fact, actually this truly models something that's happening in nature. Guys, all this stuff that we work with is really based off a true physical phenomena that's going on. And especially when we start talking about magnetism and also inductance. So I got a small little demonstration here, guys. A little bit different than I may be able to do within the class sometimes, but here we're actually going to look at a resistor. This is actually what we call an electrolytic capacitor, and that electrolytic capacitor is generally what we like to use within electronics. But there's other types of capacitors that we utilize that have more of a polyfilm in them, a little flat, but these cylindrical electrolytic capacitors, mainly at least what I've used within basically my designs that I've done. So let's take a look, and over here we got an oscilloscope that actually shows us that time varying response. Let's see if it's actually exponential. Let's charge this sucker. Well, that looks pretty exponential in nature, but up here, if we look back at the board right there shows basically an exponential decay. Let's see if we actually get an exponential decay right here. Well, oh man, look at that. That is an exponential decay if I've ever seen one, guys. Let's see that again. That's just too cool to me. Okay, there's the exponential rise. And sure enough, there's our exponential decay right there, guys. Here's the thing. Guys, that is the beauty of this stuff that we're working with, especially with differential equation analysis, is because what we just saw on that screen is in fact actually truly modeled with math. Like these higher level math courses that we take, calculus, Cal 2, Cal 3, differential equations, linear algebra, all these things are tools that help us model really what's going on in a physical system. And everything that we're working with, and especially for the electricals, we're working off basically this unique phenomena that our world is absolutely dependent upon, especially when we start talking about magnetic fields, and also how we actually operate within society. So it's kind of a unique opportunity to actually get to know a little bit about some of the most wonderful parts of nature, essentially. I mean, this stuff just gets me so stoked, and I love it. I absolutely love this material, and it's just fun to actually get to teach it. So when we come back in the next video, I'm going to show you guys how to actually solve these problems, and maybe I can actually get some of you guys to convert over into being an electrical engineer so I can get my $50. All right, see you next time.